Good afternoon, lads and ladies. Welcome back to Cal 2. Afternoon. Good morning, lads and ladies. Welcome back to Cal 2. I am sorry for my delay here. We've got some folks doing some tile work at the house, and I, if I'm honest, forgot when I woke up this morning that they were coming by, so I didn't prep. Okay, my fault. Very sorry. Today we're going to continue talking about sequences in series, specifically series. Last time, we computed a bunch of partial sums, and we're getting kind of close to understanding what series are, hopefully. And today, I'm going to do a few things. I'm going to prove to you the theorem that we finished with last time. We're going to talk about two special kinds of series. One of them is the geometric series that we met last time, and we'll prove that theorem. The other special type of series that we can work with directly are called telescoping series. We will learn about those today as well. Kind of more important, sorry, I'm messing with the French press here, trying to get some coffee together. Kind of more important than telescoping series, and arguably more important than geometric series, we're going to look at some theorems today about the convergence of series, and that's a big deal. We're going to learn our first convergence test for infinite series. First, general convergence test that doesn't depend on the series being a particular form, like geometric or something. I gotta go return this coffee, otherwise my wife will. So yeah, that's our roadmap. Let's get to it. Obviously, in chat there. That's right, and we wanted to look at some examples of limit problems today too. We can do that. Let me try to work it into the context here. This is MAC 2312, section number 004. That means we're talking about Calc 2, and today is the 13th of October 2021. Today we're looking at more series. We're going to finish 11.2 and maybe begin 11.3, which is on the integral test. But we'll see. If we don't get to 11.3 today, that's all right, but we do need to keep it moving. Last time we ended with this theorem. Geometric series. That theorem says the series S equals sigma n from 0 to infinity a times r to the n converges if and only if the absolute value of r is strictly less than 1. In that case, the value of the series will be the starting term over 1 minus the common ratio. A lot of people learn this as a over 1 minus r, and if your series begins with n equals 0, that's correct. But if your series begins with n equals 1 or 2, then the starting term is not a, but it would be ar or ar squared. So this is definitely how I recommend remembering this, right? Write it down this way. The a over 1 minus r thing can get you into trouble if you're not careful. Such series diverge if the absolute value of r is greater than or equal to 1. That's implied by the first sentence, right? Converge if and only if r is less than 1 in absolute value. But just to be clear, if the absolute value of r is bigger than 1 or equal to 1, the series will diverge. The proof, we were looking at the nth partial sum, which is a plus ar plus ar squared plus ar cubed, all the way out to the second to last term would be ar to the n minus 1. And the very last term would be ar to the n. And we said if we multiply this by 1 minus r, something nice would happen. So this would be 1 minus r times a plus ar plus ar squared plus ar cubed, and so on, all the way out to ar to the n minus 1 plus ar to the n. The magic here is going to come when we distribute that 1 minus r. And this is what I asked you guys to take a look at the end of class last time. How do you distribute 1 minus r over such a big expression? Well, you multiply the whole expression by 1, and then you subtract what you get when you multiply the whole expression by r. So this is 1 times this thing, which is a plus ar squared, ar to the n minus 1 plus ar to the n minus r times this thing. So if I distribute the r here, I have a times r as the first term, and then ar squared as the next term, right? R times ar. And I distribute this r to the ar squared, that becomes ar cubed. And we keep going. R times ar to the n minus 1 is ar to the n, and r times ar to the n is ar to the n plus 1. So we multiply the whole thing by 1, then you subtract what you get when you multiply the whole thing by r. And what you notice is that a lot of shit goes away here. I've got an a, okay. And then plus ar minus ar, plus ar squared minus ar squared. There's a plus ar cubed in here, and then a minus ar cubed here. Everything will cancel all the way up to a times r to the n. A times r to the n minus a times r to the n. The last term that survives is a times r to the n plus 1. So this is the magic of multiplying by 1 minus r. All of the dots go away. You end up, instead of having like n or n plus 1 terms, after you distribute your 1 minus r, you just have 2 terms. Now, divide by 1 minus r. So your nth partial sum is a minus ar to the n plus 1, all divided by 1 minus r. So remember, the full infinite series S is the limit as capital N goes to infinity of the capital Nth partial sum, which would be the limit as capital N goes to infinity of a minus ar to the capital N plus 1 over 1 minus r. And the only piece here that depends on n is this piece, right? A is a constant, 1 is a constant, r is a constant. The only piece that changes with n is this r to the n plus 1. And r to the n plus 1 is r times r to the n. And we know what r to the n does as r goes to infinity. There's 2 possibilities. You can go to 0 if the absolute value of r is less than 1. We can't have r equal to 1 here, right? If r is equal to 1, then the denominator is 0. That's a problem. So I'm not interested in r being 1. This blows up to infinity, or does not exist if R is larger than 1. So this piece is equal to A over 1 minus R, because this piece will go to 0 if the absolute value of R is less than 1 and does not exist otherwise. So that's it. That's your proof, right? Geometric series are one of the only series that we know everything about. We know exactly when they converge. We know a formula for the nth partial sum, blam. And in the case where they converge, we know what they converge to. This is a big deal. Most series, you'll find we can't learn this much about. Most series are hard to work with. Let me show you an example or two, and then we're going to move forward. I do promise I'll work some sequence problems in here today, or at least some limit problems in here. But first, let's investigate the series S equals sigma n from 0 to infinity 2/3 to the n. This series is 1 plus 2/3 plus 4/9 plus 8/27 and so on. That's the first few terms of that series. And by investigate, I mean figure out whether it converges or diverges. If it converges, try to find the sum. Tell me everything you can about this series. And the trick is that this is a geometric series. Is a geometric series. The common ratio R is 2/3. So the absolute value of R is the absolute value of 2/3, which is 2/3, which is less than 1. So the series converges. The sum of the series, sum or value of the series, is therefore S equals the starting term over 1 minus the common ratio. The starting term of this series, the very first term when you write the series out long form, is 1. So this is 1 over 1 minus the common ratio, which is 2/3. And we need to simplify this. That's 1 over, what is 1 minus 2/3? Well, 1 is 3/3. 1 minus 2/3 is 1/3. And 1 divided by 1/3 is 3. And that's everything, right? We know that the series converges, and we know that the sum of the series is 3. In other words, when you add up all of these infinitely many terms, what you get out is 3. Or if you want to think of it another way, the more and more terms you use in this series, the closer the sum gets to 3. Right, so working with geometric series is easy, as long as you know what you're doing. Let's do another. Here my series is sigma n from 2 to infinity, 1 over pi, negative 1 to the n times 1 over pi to the n. If I write this out long form, the first term is negative 1 squared times 1 over pi squared. That's positive 1 over pi squared. When n is equal to 3, I have negative 1 cubed times 1 over pi cubed. That's negative 1 over pi cubed. When n is equal to 4, that's going to be positive 1 over pi to the 4, and then negative 1 over pi to the 5, and so on. So we practiced this a lot last week. The kind of first skill that you need to have with these is just understanding the sigma notation, being able to go from this to this. Are there any questions about how I did that in either of these? Where those terms came from or why they look the way they do? Okay. It may not be immediately obvious, but this is also a geometric series. This is sigma n from 2 to infinity, negative 1 over pi to the n. Just using algebra rules, right? A to the n times 1 over b to the n is the same as a to the n over b to the n, which is the same as a over b all to the n. This is a geometric series. With common ratio r equals negative 1 over pi. And I want to remind you, it's not r itself, but the absolute value of r that matters. So the absolute value of r is the absolute value of negative 1 over pi. Is 1 over pi. Is this bigger or smaller than 1?
Smaller.
Smaller, right? Pi is about 3, so this is like 1/3. This is definitely less than 1. So the series S converges. The sum of the series is the same rule, starting term over 1 minus r. Now here, my starting term is not 1. This is a place where your 1 over 1 minus r or a over 1 minus r formula would fail. Because the series starts at 2, my starting term is 1 over pi squared. So that's what goes upstairs. And then downstairs is 1 minus my common ratio. And again, that common ratio is negative 1 over pi, so you need to be careful here. This is 1 over pi squared times 1 plus 1 over pi. And if we want to simplify this, we can. It's just more working with fractions. 1 is the same as pi over pi. So this is 1 over pi squared times pi plus 1 over pi. And then we can flip and multiply. So this is 1 over pi squared times pi over pi plus 1. And the pi squared downstairs cancels a little bit with the pi upstairs. You get 1 over pi times pi plus 1. Questions on either of these? Okay. So I'd like to share with you a theorem, which is our first convergence test for infinite series. Remember I said a while ago you want to dedicate a few pages in your notes to convergence tests. We are now talking about infinite series, and here is our first convergence test. This is called the test for divergence. Sometimes I call this the test for obvious divergence. Your book just calls it the test for divergence. Whatever you want to call it is fine, but you need to remember it. And the logic here is a little tricky. This says, if the limit as n little n goes to infinity of a sub little n is not 0, then the series sigma n from wherever to infinity, I'll say 0 to infinity, but it could be anything down here, doesn't have to be a 0, must diverge. Intuitively, here's what's going on. If the terms of your series don't get small, and you're adding up a bunch of shit that doesn't get small, then that sum needs to be large. That's it, right? If you're adding up infinitely many things and you want that sum to come out finite, the things you're adding up have to go to 0. And the way people mess this up, the converse is false. It is not true that lim n to infinity an being 0 implies that the sum sigma an converges. And the sum here could be from wherever, I'll write it as being from 0. Not true. So this theorem only works in one direction. If the limit isn't 0, if the limit of the an's isn't 0, then the series sigma an can't converge. All right. If the limit is 0, then the series could converge or diverge. All right. And sometimes we write that in here. If lim n to infinity an is 0, the test is inconclusive. Okay. And this will give us an opportunity to play with some sequence limits, right? Because a part of taking this, running this test, is calculating the limit of the ANs. The other note I'll make here, people tend to confuse these. Sigma n from wherever to infinity of an is not at all the same as the limit as n goes to infinity of an. These are totally different. I want to make sure we're really, really clear on that. The series is the limit of the sequence of partial sums, the limit of the SNs as capital N goes to infinity, which is not the same thing as the limit of the ANs. So please, please, please never tell me this thing is equal to this thing. They're not. They're not. They are related to each other by this theorem. That's it. So as you write your homework solutions, as you work through these problems, please, please use good notation. Do not get sloppy and lazy on this shit. I saw a lot of sloppy and lazy notation on the first test. I do not want to see that on the second test. When you put something on the page, make sure what you're writing down makes sense. If you want to scribble something just to kind of get it out of your brain and on the paper, do it off to the side. But make sure that your workflow here follows some logic. And I know it's challenging, but we must practice it. All right. There were a couple limits that I think folks were having a hard time with. So let's take a look at some of those.
Up on the top shelf, inside the trailer, there's a little small can of blue marks.
Let's investigate the convergence of the series sigma n from 1 to infinity. 1 plus 2 over n to the n. Just a funny looking series. Well, the first few terms of this series would be 1 plus 2 to the 1. The next term of the series would be 1 plus 1 squared. The next term of the series would be 1 plus 2/3 cubed. The next term would be 1 plus 2/4 to the 4, and so on. So the AN here is 1 plus 2 over n to the n. And I'm going to use the test for divergence. The theorem above. So that means I need to compute the limit as n goes to infinity of an. Always tell your reader what test you're using. I'm going to give you guys a bunch of different convergence tests for series, right? Each one of these sections that we're going through from 11.1 to 11.8 gives you a new convergence test or two. This would be the limit as n goes to infinity of 1 plus 2 over n all to the n, which looks like if we plug in infinity, this would be like 1 plus 2 over infinity to the infinity. Oh, damn, why am I getting so many fucking phone calls this morning? No. So this looks like 1 to the infinity, right? 2 over infinity is 0. What is 1 to the infinity?
1.
Not necessarily. 1 to any finite power is 1. But 1 to the infinity, this is an indeterminate power. So I chose this particular problem because we wanted to look at some tricky sequence limits. This is one of those tricky limits, right? So we're taking a limit like this is challenging because it's an indeterminate power, which is like the gnarliest form of indeterminate form. So how do you do this? Does anybody remember how to handle indeterminate powers? I posted some Patrick JMT videos a couple weeks ago about this. So the trick is, instead of working with an, because it's an indeterminate power, we're going to work with the natural log of an instead. So the limit as n goes to infinity of the natural log of an is equal to the limit as n goes to infinity of the natural log of 1 plus 2 over n to the n.
I generally have.
And one of our rules for natural logs, remember the algebra of the logarithm, powers inside can come down as multiples. So this is lim. This is why we do this. It gets rid of the power. You get lim n to infinity n times the natural log of 1 plus 2 over n. And if you try to plug in infinity for n here, you will no longer have an indeterminate power. You'll have infinity times the natural log of 1. The natural log of 1 is 0, which is an indeterminate product. So we've turned our indeterminate power into an indeterminate product by taking the natural log. The way you handle indeterminate products, which are like infinity times 0, 0 times infinity, is by shoving one of the terms downstairs as its reciprocal.
All right, yeah, this stuff here,
So what we say now is this is lim n to infinity. I'll shove the n downstairs as 1 over n because I'd rather work with 1 over n than 1 over this natural log. So I leave the natural log term upstairs.
Excuse me? I'm gonna come back about 1 and cough and grab that. It's okay if I leave my truck there? Awesome, thank you.
All right.
No, we're good.
Now, if I send n to infinity in this expression, 1 over n goes to 0, 2 over n goes to 0. This would be the natural log of 1 over 0, which is 0 over 0, which is now finally an indeterminate ratio. And once you have an indeterminate ratio, you can use L'Hopital's rule. L'Hopital's rule says differentiate the top, differentiate the bottom, and try again. The derivative of the top here is a little bit complicated. It requires the chain rule. Remember how you differentiate the natural log? It's 1 over the inside times the derivative of the inside. The derivative of 1 plus 2 over n is negative 2 over n squared. 1 differentiates to 0. 2 over n is 2 times 1 over n. The derivative of 1 over n is negative 1 over n squared. The 2 just comes along for the ride. Downstairs, the derivative of 1 over n, we just said, is negative 1 over n squared. So we've used L'Hopital's rule now. And before I plug back in, I'm going to try to clean this up. I've got a factor of n squared in the downstairs here, a factor of n squared in the downstairs here. So this is 1 over 1 plus 2 over n times negative 2 over n squared. And then I flip and multiply by this piece, negative n squared over 1. You can cancel the n squareds. And what do we get? Lim n to infinity. Negative times negative here is positive. 2 divided by 1 plus 2 over n. So all the hard work is done now. I'm going to take a second here for questions on this.
Could you go over LHOP again, please?
Like, what does L'Hopital's rule say? Or,
No, like how you simplified that.
so the side here. So let me come here, talk a little bit about the derivatives involved. So I needed to differentiate the natural log of some stuff. The way you do that is with the chain rule. The derivative of the natural log of some stuff is 1 over that stuff times the derivative of that stuff. That's the chain rule. So if I want to differentiate the natural log of 1 plus 2 over n, that's going to be 1 divided by 1 plus 2 over n times 1 plus 2 over n primed, which is 1 over 1 plus 2 over n times 0 minus 2 over n squared. So the derivative of 2 over n is negative 2 over n squared, right? Well, comfortable with that? That's 2n to the negative 1. So when you differentiate it, you get negative 2n to the negative 2, which is this. The 1 differentiates to 0. So that's where that derivative is coming from. Is that the part we wanted to see, this numerator? Then the simplification is just normal working with fractions. I leave the numerator alone, and I flip and multiply by the bottom. and then the n squared here and the n squared here cancel. So I have -2 times -1 is +2 times 1 over 1 plus 2 over n. That's 2 over 1 plus 2 over n. Any other pieces we want to look at here? All right, then. As n goes to infinity, what do we get here? Well, as n goes to infinity, 2 stays 2, 1 stays 1, and 2 over n goes to 0, right? 2 over infinity is 0. So this limit is 2. But I'm not done yet. This isn't the limit of the ANs that I'm working with. It's the limit of the natural log of AN. So from here, we would say, since the natural log of AN goes to 2, AN itself goes to E squared. That's how you undo a natural log, right? You exponentiate. Now we're almost done with the series problem. We are done with, if you want to think about like practice with sequences, right? This part right here is practice with sequences. We're just taking a limit. But remember why we were taking that limit. We were using the test for divergence. So to finish the actual problem we're looking at with that series, we would say this. Since the limit as n goes to infinity of AN is E squared, which is not 0, the series S equals sigma n from 1 to infinity, AN, which is my series, sigma n from 1 to infinity, 1 plus 2 over n to the n must diverge by the test for divergence. Again, as you work your homework problems, mimic what I'm doing here. In particular, please write in full sentences and check your logic. Right? Don't just put the symbols on the page. With this section, with this whole chapter, it's the logic that matters. Our theorem says if the limit of the ANs is not 0, then the series sigma AN must diverge. Here, my series was sigma 1 plus 2 over n all to the n. And we found that the limit of this guy was E squared. So the series sigma that guy must diverge, because basically you're adding up, I mean, the first few terms don't look anything like E squared, but the tail of the series, which is the stuff that matters, the values, the parts of the series that come from very large values of n, you're adding up like E squared plus E squared plus E squared plus E squared plus E squared. E squared is about 9. So this is like adding up 9 plus 9 plus 9 plus 9 infinitely many times. Of course that's going to diverge. Of course that's infinity. Okay. So that's our first example of a series we can approach with the test for divergence. The limit there is quite tricky. That's not always going to be the case. I don't want time, 10:13. All right. We need to take a look in 11.2. We still need to talk about telescoping series. Turn this back on. So before we talk about telescoping series, take a look and see if there's anything else in here that's worth playing with. Definitions, geometric series, telescoping series. And is the test for, oh yeah, rules for series. Yeah. So, rules for the sigma operator, the algebra rules. They're the same as integrals. Same rules. So I'm going to adopt a convention here. When I want to make a statement that's true about series in general, I'm not going to write the n equals 0, 1, or 2, or whatever down here. I'm just going to write sigma. All right, you'll notice your textbook here. Well, we'll do it. All right, whatever. It gets to be a hassle because we want to make sure that it's clear that all of these things are true for any series. But let's do it. Okay, if sigma n from wherever, I'll do 0. How about that? And sigma n from 0 to infinity of bn both converge, then sigma n from 0 to infinity of an plus or minus bn is the same as sigma n from 0 to infinity an plus or minus sigma n from 0 to infinity of bn. So you can split series up over addition. Also, sigma n from 0 to infinity k times an is the same as k times sigma n from 0 to infinity of an for any constant k. Right, so series, the rules for manipulating series are the same as the rules for manipulating integrals. It's a linear operator. You can split it up over addition and subtraction, and you can pop out constant multiples. Right, that's what this is saying. They took the plus and minus and write them separately. They started at 1. It does not matter. All right. Okay. The next thing I'd like to look at some telescoping series. So there are kind of two families of series where we can do all the stuff, where we can find a formula for the nth partial sum, where we can find the sum of the series. We can say exactly when the series converges or diverges. Those are geometric and telescoping series. The name telescoping series comes from those old like pirate telescopes, you know, in cartoons. You'd see some guy up there on the mast and he sees something and he says, land, oh, whatever, and then he collapses his telescope. Put it up, and the whole long telescope like collapses into itself into a nice little thing you can put in your pocket and walk away. Telescoping series are like that. You've got a big long series that when you look carefully at it collapses into a very small series, finitely many terms. Now, what we really are going to be looking at isn't the full infinite series, but it's partial sums. So these are series with a lot of cancellation. Additive cancellation. And the way we work with them, we write out the capital Nth partial sum. Okay. I put a few of these in your homework. Let me grab one here that is easy-ish to work with to begin. Let's look at this guy. I'm going to write this down, and then we'll come back to the doc cam. Same thing, we're going to investigate the series S equals sigma n from 1 to infinity e to the 1 over n minus e to the 1 over n plus 1. A lot of your telescoping series, you'll need to do some partial fractions or something else first. I'm choosing this example because it's an example where we don't need to do partial fractions to get started. Okay. if I write out the first few terms of this series, this is e to the 1 minus e to the 1/2. And then the next term is e to the 1/2 minus e to the 1/3. And then you'd have e to the 1/3 minus e to the 1/4, and so on. And what you see is like the e to the negative 1/2, or sorry, the negative e to the 1/2 and positive e to the 1/2 would cancel. Negative e to the 1/3 and positive e to the 1/3 would cancel. This is what I mean by a lot of additive cancellation. The question is, what's happening in the ellipses? What's happening out here in the tail of the series? Because that's the part that matters. The way we find it is by writing out the nth partial sum. So if you have a series with a lot of cancellation term to term, then you're going to write out the nth partial sum, which remember is sigma 1 to capital N, e to the 1 over n minus e to the 1 over n plus 1. And you literally just write it out. So it's like this, but it ends. So the first term is e minus e to the 1/2. The next term is e to the 1/2 minus e to the 1/3. The next term is e to the 1/3 minus e to the 1/4. And then you've got some shit going on in here. The big deal is that this is a finite sum. So it ends. The second to last term is e to the 1 over capital N minus 1 minus e to the 1 over capital N. And the very last term, which I don't quite have room for here, is e to the 1 over capital N minus e to the 1 over capital N plus 1. And then we simplify. So what goes and what stays? Well, e to the 1/2 goes. There's a positive and a negative version of that. E to the 1/3 goes, positive and negative versions of that. The e to the 1 over n's go, positive and negative versions of that. What about this guy? Does this negative e to the 1/4 live or die? The question is, in the dot dot dots here, is there a positive e to the 1/4 term that would cancel this guy? That's the question. So what's the very next term of the series in here? This was my little n equals 1 term. This is my little n equals 2 term. Little n equals 3 term. What does the little n equal 4 term, the next term of that series, look like?
E1 over 4 minus E1 over 5.
Perfect. Yeah, the next term in this dot dot dots that's hiding there is e to the 1/4 minus e to the 1/5. So he is going to get gobbled up by the next term in there. Okay, this is my little n equals capital N minus 1 term. This is my little n equals capital N term. What about this guy? Positive e to the 1 over capital N minus 1. Does he live or die? Is there a term hiding in the dot dot dots that would cancel him? It does get canceled. Yes, it gets canceled by the negative part of the term immediately before it. The little n equals capital N minus 2 term is e to the 1 over capital N minus 2 minus e to the 1 over capital N minus 1, which has a negative version of this guy. So he also goes. So what lives? Well, this very first part of the first term, e, he survives. And the negative 1, e to the 1 over n plus 1 survives. So we found a nice formula for the nth partial sum. The capital Nth partial sum simplifies to e minus e to the 1 over n plus 1. Therefore, since the full series S is the limit as capital N goes to infinity of the capital Nth partial sum, and I now know that the capital Nth partial sum is e minus e to the 1 over capital N plus 1, the full series S is equal to that limit. Again, not an. The series is not the limit of the an's. It's the limit of the partial sums, Sn. All right, as capital N goes to infinity, 1 over capital N plus 1 goes to 1 over infinity. So this is e minus e to the 0. Right, 1 over n plus 1 goes to 0. So that's e minus 1. And now, just based on the definition of an infinite series, the full infinite series is by definition the limit of its nth partial sum. If that limit exists and is finite, the series converges. So S equals sigma n from 1 to infinity e to the 1 over n minus e to the 1 over n plus 1 converges and has value S equals e minus 1. That's it. So telescoping series are very nice. Right? They're very nice. The trick is to write out the nth partial sum. This is all the work, right? All the work is right here. You have to remember your definitions, but nothing more is required. Other telescoping series, the most common way telescoping series show up, let me show you, are these, right? And what you see here is like a lot of stuff where you could do partial fractions. So I can take a look at one of these, 1026, yeah. Let's take a look at number 43. This will be the last telescoping series we look at. If you start writing out the terms here, it's not at all obvious that this is telescoping. Right? The first few terms in this series are 2 over 4 minus 1, it's 2/3, plus 2 over 9 minus 1 is 2/8, plus 2 over 16 minus 1 is 15, and so on. But when you look at this guy, you realize, oh, I can factor that bottom and maybe do some partial fractions. So an here is 2 over n squared minus 1, which is 2 over n minus 1 times n plus 1. So we can set up some PFD. 2 over n minus 1 times n plus 1 as a over n minus 1 plus b over n plus 1, which means 2 is equal to a times n plus 1 plus b times n minus 1. And at n equals 1, we get 2 equals 2a. So 1 is equal to a. At n equals -1, we get 2 is equal to b times -2. So -1 is equal to b. So all of this means that an can be rewritten as 1 over n minus 1 minus 1 over n plus 1. Which means that my series S is sigma n from 2 to infinity, 1 over n minus 1 minus 1 over n plus 1. And now if you write out the terms of the series in this form, you'll start to see that it looks like we're just going to telescope. When little n is equal to 2, this is 1 over 1, which is 1, minus 1 over 3. When little n is equal to 3, the next term of the series, this is 1 over 2 minus 1 over 4. No cancellation yet, but when little n is equal to 4, you get 1/3 minus 1/5. All right, a couple more. When little n is equal to, let's see, 2, 3, 4, 5, we get 1/4 minus 1/6. And one more would be 1/5 minus 1/7, and so on. So we do have some telescoping going on here. I've got a negative 1/3 and a positive 1/3, negative 1/4 and a positive 1/4, negative 1/5 and a positive 1/5. The cancellation isn't as obvious as in the last one, because it's not that this term is canceling with the immediate next term, it's canceling with 2 guys down the road. But we're still going to get a lot of cancellation. The challenge, as always, is to figure out what's going on in the dot dot dots. So instead of looking at the full infinite series S, we need to look at the nth partial sum. Here's a suggestion. Look at the gap between the denominators. So the gap from n minus 1 to n plus 1 is 2. Write one more term than the gap size. So I'm going to write at least the first 3 terms and at least the last 3 terms when I write out Sn. Give myself some space. Sn is 1 minus 1/3 plus 1/2 minus 1/4 plus 1/3 minus 1/5 plus dot 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 plus. Now the last 3 terms, when little n is equal to capital N minus 2, this is 1 over capital N minus 3 minus 1 over capital N minus 1. When little n is equal to capital N minus 1, I have 1 over capital N minus 2 minus 1 over capital N. And when little n is equal to capital N itself, I have 1 over capital N minus 1 minus 1 over capital N plus 1. This is the nth partial sum. This is the n equals 2 term. This is the n equals 3 term. This is the n equals 4 term. This is the n equals cap n minus 2 term. Little n equals cap n minus 1, and little n equals cap n. I write 3 terms at the start and 3 terms at the end because my gap size here between these denominators was 2, and that's the minimal amount you can write to see the cancellation pattern. Of course, if I had 4 terms and 4 terms, that might be nice, but this is enough. So who lives and who dies? Well, here's a negative 1/3 and a positive 1/3. And what's the pattern? The negative version, the negative portion of a given term cancels with the positive portion 2 terms later. So here I have a positive 1/2 and a negative 1/4. Do either of these get canceled by something in the dot dot dots?
Negative 1/4.
Good. The negative 1/4 gets canceled by the positive portion of the little n equals 5 term, the first thing in the dot dot dots. So this guy is going to go, and the thing that gets him is the first term in here. What about the 1/2? Is there a negative 1/2 somewhere to cancel with this guy?
No,
No, there is not, right? He would have had to have come from the negative part of the term before this one, but there wasn't a term before this one. We do the same thing in the tail. So what lives and what dies? Well, I see a n-1, 1 over n-1 negative here, 1 over n-1 positive here. Those clearly go. What else can we say? Let's look at, for example, this guy, positive 1 over n-3. Is there going to be a term to cancel him?
Yeah, 2 before him.
Good, 2 before, right? So the term right before this is 1 over n-4 minus 1 over n-2. And the term right before that is 1 over n-5 minus 1 over n-3. So he gets killed by something 2 back. How about these guys? Who lives, who dies? Who does the killing?
1 over n.
What happens to 1 over n?
Well, it would cancel with the term capital N plus 1.
Well, there
Or
is no capital N,
stopping,
so
yeah.
you're right. Yeah, if there was a next term here, that would cancel this, but we're looking at the nth partial sum. So there isn't a term down here to cancel. So he's going to live. What about him?
it would cancel.
He would cancel with which term? Little n equals what?
Capital N minus 3.
Very good. He cancels with the little n equals capital N-3 term, the first guy before this. So this guy is going to go. And he's going to go from the term immediately before that. Okay, is anything missing? Is there anything here that's unaccounted for?
Down negative 1/5.
Very good. Does he live or die?
Die.
He dies, right? Why?
With it would be n equals 6 term.
Very good. Yes, the positive part of the little n equals 6 term, which is hiding in these ellipses. So he's going to go and he's going to be killed by the, not the term right after this, but the one right after that. So now we can write down what Sn is without any dot dot dots. Sn is 1 plus 1/2, those two survived, minus 1 over n, minus 1 over n plus 1. Therefore, the full infinite series S is the limit as capital N goes to infinity of S sub capital N, which is the limit as n goes to infinity of 1 plus 1/2 minus 1 over cap n minus 1 over cap n plus 1. And these pieces both go to 0. So this is just 1 plus 1/2, which is 3/2. So this series, S equals sigma n from 2 to infinity, 2 over n squared minus 1, converges and has value S equals 3/2. Again, pay attention to the language, make sure you're comfy with the definitions. I'll tell you one thing here that I think is important to keep in mind. Telescoping series are the only series where we work directly with the partial sum. All right, all the other series we're going to look at, we get at them indirectly. The geometric series, we use our theorem. All the other series will use convergence tests. We won't be able to say what the sum of those series are. But telescoping series, we work directly with the partial sum. So this is the only time the only ones where we write the full series is the limit as capital N goes to infinity of the SNs, which again, I want to emphasize is very different from the limit as little n goes to infinity of the ANs. Right? The only time you look at this guy is when you're using the test for divergence. And the only time you look at this guy is with a telescoping series. All right. We're a little short on time, but I'd like to solve at least one more problem for you here. And let's do something like 63 looks fun. Is there anything else that we can play with like this that's worth looking at? Nah. All right. Yeah, how about 63? So let's find the values of x such that the series sigma n from 0 to infinity e to the nx converges. The trick here is to recognize that this is actually a geometric series. Just doing some algebra, that's the same as e to the x all to the n. This is a geometric series with common ratio r equals e to the x. So r is not a constant here, it depends on x. We want to look a little bit more back here. I can hold here just for a second. Maybe while I'm doing this, so I had a request to look at this page for a little bit longer. One thing that I want to caution you guys against, a lot of people get into this habit of saying, so it converges. Don't do that. Don't use pronouns for series. Tell me what converges. This series converges. All right, I'm going to go back in just a few seconds. Okay, returning to the current example now. So the trick to sorting out this problem, finding the values of x for which this infinite series converges, is to recognize that it's a geometric series. You can do some algebra. E to the nx is the same as e to the x all to the n. You could also write it as e to the n all to the x, but that doesn't help us. The common ratio here is e to the x, right? You've got some shit to the n being summed, so that series is geometric. Therefore, S will converge if and only if the absolute value of r is less than 1. Which is the same as saying the absolute value of e to the x is less than 1. And now we have to work with some absolute value inequalities. The absolute value of e to the x is less than 1 means -1 is less than e to the x is less than +1. When is this true? Well, here's the graph of e to the x. Here's -1, and here's +1. So for what values of x is e to the x between -1 and +1? Well, e to the x is never negative. So I'm looking at here, this portion of the graph solves that inequality. Which means we're looking at x values that come from this interval. So this if and only if x is less than 0. Okay. So the series converges if and only if x is less than 0. All right, this is where we're going to end for today. I hope that by taking the time to slow down here a little bit in 11.2, I think this might be the third lecture we've spent in 11.2, we have established a good foundation for you with infinite series. Next time, we're going to talk about something called the integral test, which relates an infinite series to a type 1 improper integral in a way that is very intuitive. From there, I'm going to give you 2 different comparison tests, then something called the alternating series test, then something called the ratio test, then something called the root test, and then we will be ready for exam 2. Okay, so there's a lot of stuff here. I know we didn't get to practice a whole lot with sequences. If you want more practice with sequences, come by my office hours, post to the Discord, let me know what you want to see, and I can try to put some stuff together for you. But this is where we are now. And so my advice to you, if you feel at all uncomfortable, get in here into the book. Remember, mathematics is not a spectator sport. You got to get your nose in this shit if you want to feel good about it. Get in here and solve these fucking problems. There's lots of them. I would suggest, especially if you feel at all uncomfortable with this, that you solve every problem in 11.1 and every problem in 11.2. I know it's a lot, but you chose to be here. You're here in Calc 2 now. This is a hard class. You don't need to solve all of these difficult theorem proving problems, stuff like that, AMGM stuff. But if you want to get to a place where you are rock solid on this test, you got to get at least up to like 71. Right? That would be my advice. Definitely solve everything on the first page, both exercises in 11.1 and 11.2. I can't assign all of these. If I assigned every single one of those problems, someone would track me down at home and stab me in the chest. I understand that. I can't require all of you to do all of this, but I can strongly encourage those of you who want to do well on the next test to come in here and solve at least the first page of exercises from 11.1 and 11.2. If you want to be good at this shit, that's what it takes. And I promise you it's doable, and I'll help you if you get stuck with anything. So please put the time in, all right? I'm going to take a look today. I might add a little bit to your homework. Let me see where we're at with that before I wrap things up. Come on, Weathersign, you can do it. All right, if necessary, I can extend this a little bit. So I already did. Yeah, so your 11.2 part 2 isn't due until the 18th. I'm giving you time to work on this, but I want you to work on it now. All right, if you have not finished these, you must be done with homework 7, like today or tomorrow. No excuses for not getting in here. And by being done with this, I mean, not just putting the right answers into WeatherSign, but thoroughly understanding all the problems. Okay, it's going to take some time. It's not going to be obvious or easy, but you can do it. So get in here, grind on this stuff. If you need help with any of these things, come see me in office hours. It's not impossible. It is kind of hard, but I know you can do it. I see there's some repetition. That's okay. Okay, that's it from me, guys. I will see you either in office hours or on Friday. Please work hard on this stuff. I think you've got enough from 11.2. So next time we're going to talk about 11.3, and then I'll send out your next homework. Okay?
Professor, can I ask a quick question?
Sure.
So I rewatched the last lesson because I wasn't feeling well. So at the beginning of the lesson, I asked myself a question. What is the difference between a series and a sequence? Is a series an addition of AN? And then I said, no, a series is the additions of N in AN. Is that correct?
You're right the first time. A series is what you get when you add up all of the ANs. So
Okay,
A1
got
plus A2 plus A3 plus A4 plus A5 all the way up, that is your series. And then the sequence is just the list of those terms, A1, A2, A3, A4, and so on. So
Got
I
it.
think a
Thank you.
sequence is like a function, and a series is like an integral of that function. That's kind of the intuition. Series are like type 1 integrals. Sequences are like the function that you're integrating. That's the idea.
Got it. Thank you.
Of course, of course. Alrighty, gang. I'm gonna head out. Take care. I'll see you on Friday.